Okay, welcome everybody. Last day of the workshop. Thanks a lot for staying with us. It's a pleasure to introduce Elisabeth Ullmann from the Technical University of Munich, and she's going to be talking to us about particle dynamics for rare event estimation with PDE-based models. Go ahead, please, Elisabeth.
Thank you very much, Omar. I think I cannot see you, but I hope that's your voice. Well, thank you very much for inviting me to this workshop. I do apologize that I cannot be here at the Newton Institute with you. I tried to join as many talks as I could, and I already enjoyed a very pleasant talk, so I'm enjoying this workshop very much. I will be talking about rare event estimation for PDE-based models. And I will also try and make the connection to Bayesian inverse problems, which is, I think, more the flavor of the workshop. But I think there's actually interesting connections between the two. But before I get started, I would like to acknowledge the following people. So I'm mainly presenting the work of Fabian Wagner and Konstantin Althaus. So Konstantin Althaus was a master student with me at TUM, and Fabian Wagner with me at TUM, who is now on. And finally, I also want to thank my long-term collaborator, Yasun Papayannou, who works in the civil engineering department at TUM. And Yasun got me interested in rare event estimation 10 years ago, and we have been collaborating ever since. Okay, and today I will give you an update. So some of you in the audience might have heard parts of the talk already, but there is also a new bit towards the last 10-15 minutes, I hope. So the plan for the talk is to quickly introduce the problem and talk a little bit about, well, the problem is estimation of the probability of failure, and then I want to talk about how we can actually approximate this probability of failure. And then I want to talk about two methods that can be used for this. And interestingly, these methods have been used for Bayesian inverse problems first. So the Ensemble Kalman filter, you might know, is used for Bayesian inverse problems, but we can actually also use it for event estimation. And a more recent method, consensus-based sampling, again used for Bayesian inverse problems, and we adapt the method to use it for rare event estimation. Okay. So let's get started with the problem. So we want to estimate a probability, which is usually attached to some engineering system. And the states of that engineering system are described by a so-called limit state function, G. And the G takes parameter values, little u here, in a potentially high-dimensional space, Rn, so the dimension is n. And then, depending on the value of that limit state function, you know that your system has failed or not. Yeah? So if the limit state function takes on negative values or zero values, then you have failed, and this indicator function here in orange will be equal to 1. And so this failure state counts. Yeah? And in all other cases, when the limit state function is positive, the function will be 0, and you don't have a failure event, you have a safe event. And yeah, so that is the main object that is used in engineering reliability analysis. And what we also assume is that these the parameter values, or this random parameter vector actually follows the standard normal distribution. And so this phi n is the standard normal density in n dimension. And this is a common assumption in engineering reliability analysis. And I think it was already mentioned in talks at the beginning of the week. If you don't have a normal distribution here, then you can transform most of to a standard normal distribution. So this is the setup, and what we are now interested in is estimating the probability that we have system failure. Now, to give you a picture what this limit state function is about, you see here the case n equal 2, so two-dimensional parameter space, and the circles are the contour lines of the standard normal density. And the limit state function, or a contour line of the limit state function you see here, when you follow my pointer, and the black line is exactly the contour line of the limit state function where it's exactly equal to 0. Yeah? So this is the boundary between the failure and safe domain. And the blue part is now the failure region. And we are interested in the probability mass of this blue region here. And the measure that we use is the standard normal density. Yeah. This picture is an exaggeration of reality. Normally, we would expect that this probability mass of the failure region is extremely small. Yeah? In realistic applications, we would hope that maybe in 99% of the cases you are safe. So Roger Garnin mentioned that already in his presentation yesterday. So where he had like an inner loop where you want to assess the reliability of the system. And I'm concerned with this basic task. Yeah? And well, what are now the challenges? In real applications, you cannot really write down this failure domain that was colored blue. Yeah, so it's typically not known in closed form. And one of the reasons is that the evaluation of the limit state function typically requires, well, it is connected to a physical model which involves, for example, a partial differential equation. Yeah, so if I want to study the safety of a nuclear repository and I want to like calculate travel times and the probability that leaked particles come out of a certain safety zone, then I have to solve a PDE, and my limit state function I can only evaluate if I solve a potentially very expensive PDE model. Yeah? And this is like two challenges. And the other common challenge that you have in realistic applications is that we have a high-dimensional parameter space. So the two-dimensional case that you have seen on the slide before is again for illustration purposes. But this n here can be quite large. Now, what can be done to approximate this probability of failure? I don't give you a full review of methods. I want to focus on sampling-based methods because the two methods I will talk about later are sampling-based approximation. Now, what comes to your mind maybe more or less immediately, and this is also a UQ workshop, so maybe I can be quick on this. What comes to mind is a Monte Carlo estimate of this probability of failure. And if we go back to this two-dimensional picture here, what this means is I give you darts that you can throw, and you throw the darts towards this plane here, and you throw the darts according to the standard normal density. Yeah? So most of the darts will land near the origin here, and then as you move from the origin, less and less darts will land there. Yeah, and then you basically do a very basic thing. You count the number of darts that hit the blue region, and then you divide the number of darts that hit the blue region by the total number of darts. Yeah, and this is a Monte Carlo estimate of the probability of failure. Now, in reality, it will be very hard to hit this region. Yeah, because this region is quite small, or it has a small probability, and yeah, this becomes very quickly infeasible because every dart costs you something. Yeah, throwing one dart costs you a PDE solve of a potentially complex model. Yeah? So the classical Monte Carlo estimate is intractable in the PDE-based application. And the major problem, you can also phrase this mathematically, this crude Monte Carlo estimate has relative means per error, which scales like the inverse of the square root of the probability of failure. So in the safety critical applications where this probability of failure is very small, you need an infeasible amount of samples in order to get a useful estimate for the probability of failure. There is many methods how you can address this problem, sampling-based methods, and I will mainly be talking about importance sampling and sequential importance sampling. There's also other methods, and I just want to give you the references. There's subset simulation, which can also be seen as a generalized splitting method. There is line sampling approaches, and then pretty much for all of these approaches, there's also multi-level or hierarchical sampling procedures, and that's actually one of my first works together with Jason, where we devised a multi-level type subset simulation approach. And multi-level here means that we use PDE models with different resolution in order to estimate this probability of failure. And because we make the samples cheaper, we can hope that we will not exceed our computational budget so fast. So, I mean, all these sampling methods that I mentioned here, they basically improve basic Monte Carlo by the fact that they need fewer samples to get a useful estimate. But even if I manage to use fewer samples, they might still be expensive. And this is where this multi-level or multi-fidelity idea comes in. But, excuse me, I also want to point out that in this talk, there will be no multi-level estimate. Yeah, I just want to mention. Okay, so what is the core concept between the methods that I will discuss later? It is called importance sampling. And mathematically, the idea is quite basic. There is a change of measure behind. Yeah? So here on this slide, you see again the probability of failure that I want to estimate. And I have my standard normal density here. I create samples according to the standard normal density, and then I count how many times I hit this the failure region. And now the idea is to actually change this measure, not sample according to the standard normal density, but sample according to a more suitable density. And a density which ensures that we hit the failure domain more frequently. Yeah? And this density is called importance sampling density, that is denoted in blue here. And well, if we are free to choose this importance sampling density here, that is point number 1, and point number 2 is if we change the measure with respect to which we sample, then we make a mistake, yeah, and we have to correct this. And that's the reason for this orange factor here. So the W is the so-called importance rate or likelihood ratio. This is like a correction factor that we have to plug into this into the integrand here. Yeah? So we sample with respect to another more suitable density, and we correct our integrand. And now the big question is, what is a suitable density? Well, there is actually a so-called optimal importance sampling density, which would give you a zero variance Monte Carlo estimator. And this optimal density you can see on the slide. So it's our nominal density or standard normal density here. But then it is actually multiplied with the indicator function that indicates the failure. And the denominator here, 1 divided by the probability of failure, is a rescaling, so that we have a density, yeah, that integrates to 1. And now this optimal importance sampling density tells you something interesting, because it is supported on the failure domain. So it looks like our standard normal density, but it's actually supported in the domain that we are interested in. Yeah? And so this is a very good importance sampling density. But maybe you already can imagine that this optimal importance sampling density is actually not accessible, yeah, for the same reasons that I mentioned before. So in order to sample from the density, number 1, you need to know the failure domain, which we don't know in closed form. And what's even worse, you also need to know the probability of failure that you want to estimate in the first place. Yeah? So in that sense, what we are going to do, we will use this optimal importance sampling density as a guidance. Yeah? We will not be able to sample directly from it, but it tells us something which densities could consider. And now the idea is to actually do this sequentially, and that's the idea of the so-called sequential importance sampling. So we construct a sequence of auxiliary densities which gradually approximate this optimal importance sampling density. And well, how do we do this? We start with samples according to our standard normal density. And then we take these samples and transform the samples in a suitable way so that we get samples from a different density that I call P1 here. And then we repeat this step with another auxiliary density P2, and then we continue until we realize that we are suitably close with our density to the optimal importance sampling density. Yeah? And now this sequence of auxiliary densities already tells you a little bit about the link to Bayesian inverse problems, because in a Bayesian inverse problem, you have a very similar task. So most of the sampling-based methods for Bayesian inverse problems actually start by sampling from the prior distribution. And this is a distribution that is known, or you assume that you can generate samples from that. And then you do intermediate steps, so-called tempering steps mostly. So you you construct a sequence of intermediate densities, and then finally you will hopefully approach the posterior density. Yeah, so there is really a very nice connection to this nominal density in importance sampling and the prior density in a Bayesian in this problem. And on the other hand, we have this optimal importance sampling density. And in a Bayesian inverse problem, that would be the posterior density. Yeah? And that was the main motivation for us why we take methods from Bayesian inversion and apply it for the event estimation. Now, in this talk, the two methods I will present share the same key idea. The difficulty is to actually construct these intermediate densities, or basically to generate failure samples using samples from the standard normal distribution. Yeah? So it's very difficult to hit the failure domain. So this first step, generation of failure samples, is the difficult bit. And we do this by moving an initial ensemble of particles towards the failure domain along the trajectories of a suitable stochastic differential equation. And once we have particles that are near the failure domain, then we use this ensemble for importance sampling. And I also want to point out at this stage the advantages of this approach. So normally, for example, in Bayesian inverse problems, you would maybe use some Markov chain Monte Carlo method to generate posterior samples. And Markov chain Monte Carlo methods are also used in rare event estimation. Yeah, I mean, you can apply it, and it's perfectly fine. But in my experience, it is a bit difficult to tune these parameters. And if we have an SDE dynamics behind the particle movement, then, well, I don't have to tune my NCMC. And what I also like about this idea of generating samples with the help of stochastic dynamics is that we can hopefully use established SDE theory and discretization methods. But maybe I should also give you a warning. I'm not at all an expert in SDE theory. Yeah, and well, so I'm learning this as we go along. But I find it interesting, and hopefully you also find it interesting. So what do we want to do in a picture? So here you see again a two-dimensional parameter space, and if you follow this hand here, the cursor, this is the boundary of the failure domain. This is a common test example in civil engineering. And so the failure domain is here in the upper right part, and the safe domain is here. And we basically start with samples from the standard normal density. So the origin is here, and we would start with samples that are very much concentrated near the origin. And then we want to move these samples with the help of discretized SDE towards the failure domain. And then we use a suitable stopping criterion to stop our iteration, and then we can take these particles in an importance sampling set. So that's basically the idea. And oops, sorry. Right, and I already pointed out this connection to Bayesian inverse problems. The first method I will talk about, the Ensemble Kalman filter for rare events, is actually based on the Ensemble Kalman filter for inverse problems. That is used to generate samples of the posterior distribution. And we adapted this so-called A key to the rare event estimation problem. That helps us to generate samples of this optimal importance sampling distribution. or I will point out that actually this is not always possible, but that's at least the idea. And in the second method, we use the so-called consensus-based sampling that was recently introduced by Jose Carrillo, Franca Hoffmann, Uran, and Andrew Stewart. Again, in the context of Bayesian inverse problems, and then we adapted this method for Ray event estimation. Okay, now I think we are ready to talk a little bit about this Ensemble Kalman filter for Ray events. And well, as probably some of you in the audience know, the ENKF is used to solve an inverse problem, where I have a parameter to observable map, and I have observations which are polluted by noise. And a typical inverse problem would be this equation that I'm pointing out here. So I have a parameter to observable map. The parameters are u. Then I plug that into my parameter to observable map, and I get observations that are denoted with y here, and then they are disturbed by additive Gaussian noise, I'm assuming. So that would be an inverse problem. Now, how can we connect this actually to Ray event estimation? And the idea is simple, and that was Fabian's idea. So we define an auxiliary limit state function. So if you maybe recall, this g of u was our limit state function that distinguishes the safe and the failure domain. And now this g tilde is defined as the maximum of 0 and g of u. And basically what this g tilde is doing, it's well, if we are in a failure state, then this function will be 0. And if we haven't failed, then this g tilde of u will not be 0. So with this maximum, we basically translate this inequality condition into an equality sign. Yeah, this is really what's behind it. Yeah, so the failed states are states where g of u is less than or equal to 0, and now we transfer this so that the failed states correspond to 0 values of this g tilde. Yeah, and so without noise, this equation here can tell us exactly where the failure states are. Well, also assuming that we use artificial observations, the artificial data is simply 0. And the prior measure that we use is our standard normal density, the nominal density in our reliability problem. And now we are ready to actually solve this auxiliary inverse problem, and it can be done using the Ensemble Kalman filter for inverse problems. And again, the two steps that we have in mind here, so this A-key iteration is used to move the samples which are initially distributed according to the standard normal distribution, move them towards the failure domain, and then we can use the samples together with important samples. So now maybe this looks a little bit artificial to you. Yeah, what's the importance of A-key? I mean, do we really have to do this? Yeah. Apart from the fact that it's an interesting idea, I think. Well, actually, it's not so artificial as it looks like in the beginning, because actually you can show that the auxiliary densities that are associated with an A-key iteration actually converge to the optimal importance sampling density. Yeah? So there is a link that we can exploit. So here in that box, you see the auxiliary densities with the Eki iteration. If I just apply my Bayesian inverse problems framework and look at posterior measures, and if I translate this to our auxiliary inverse problem, I get auxiliary densities that have the following form. So we have here the standard normal density that is multiplied by the exponential of minus, then a scaling factor, and then I have this auxiliary limit state function g tilde squared, and sigma is a temperature parameter here. And then I also have this normalization constant, like which would be the model evidence equation. And now the idea of Eki is to actually start with the initial temperature sigma 0 equal to infinity, and then we basically have again our standard normal density, Cn here, and then we gradually decrease that temperature, and this will then actually, in our case, lead to the indicator function. Yeah. So what we are doing here is we are essentially approximating the indicator function that indicates the failure domain. And maybe in the interest of time, I can skip the details, how this is implemented. I mean, I can just show you this slide very quickly. So we really implement this Eki iteration as it is done, as it was done already by Marco Iglesias and co-workers, or also in the paper of Claudia Schillings and Andrew Stewart. So there is really nothing new, and the only bit is that we work with this auxiliary limit state function. So that's exactly the same thing, and we can also adapt this temperature parameter and choose it adaptively, and this has also already been done for Eki by Marco Iglesias, and for the sequential importance sampling for the event estimation that has been done in the paper by Yasa. And yeah, if you want to know the details, yeah, we can talk about it later. I think it's maybe useful to look at the picture again. So this picture you have seen already. Again, this two-dimensional parameter space. And now maybe you have a better idea what's actually going on here. So here you see the particles at the final Eki iteration. So this is the particles that you get when you stop this Eki iteration. And we use different stopping criteria here. So we basically compare, or we use as a stopping criterion the effective sample size here. And in our case, it translates to how many particles are actually in the failure domain. Yeah. So here with the yellow ensemble, maybe you see that not so many particles have reached the failure domain already, and then with red and blue, more and more particles have reached the failure domain. Maybe I should also point out that because of this Eki dynamics, the particles will move towards the failure domain, and because of the observational noise, well, and if there was no noise, particles would actually stop and get stuck here exactly at the failure surface. But because there is also some noise, they actually move also a little bit into the failure domain. And this is a really interesting feature that you can actually find, or that the particles actually get stuck to this surface here. On the right-hand side, you see this approximation of the indicator function that I mentioned. So the function that indicates the failure states is this indicator function here that I'm pointing out with my cursor. And the approximation that is generated by the ENKF is now a one-sided approximation of the indicator function. Actually, in the failure domain, the approximation is exact, and outside, it's not exact, but maybe you can see that these curves approach this step function. And that depends on this temperature parameter sigma. Okay. So one problem we have with this EKI iteration is that it has been known already for a long time that this final EKI ensemble is actually not able to approximate this optimal importance sampling distribution very well. Yeah, so I mean, it's known for Bayesian inverse problems that these EKI ensembles are actually not distributed according to the posterior density. Yeah, so you get quite a good approximation of the posterior mean, but already for the covariance, the approximation quality is limited, and yeah, we have the same feature here. Yeah, so ENKF Fourier events inherits this feature. And well, what we do in order to address this is we use the final particles in this final ENKF step, and then we fit a distribution model so that we can actually apply importance sampling. And we fit, well, either a Gaussian mixture distribution or a mixture of a Mises-Fisher-Nakagami distribution model. And details are in the paper. And the point why we have to do this is because we really do not know the distribution or approximate distribution of this final EKI ensemble. Yeah. And if we do not know this distribution, then we cannot do importance sampling. Okay, so in the that was published last year in JUQ, you find more experiments with the PDE-based limit state function in up to 150 dimensions, 2D physical space. You also find an explanation how we do this adaptive choice of the temperature parameter sigma k. What is also very interesting for us, and we didn't investigate this fully, I mean, we implemented it and didn't do more investigations, is that we can actually also treat multimodal failure domains. So the example that I showed you is a unimodal failure problem, so to speak. So you only have like one safe region, and then a clear-cut distinction between safe and failure region, and the EKI particles will concentrate near one point. So this is known. This is due to the EKI dynamics. But sometimes you will have a multimodal failure problem where you have different points in your parameter space that are associated with failures. And in order to treat this, we use a technique that is also available for this EKI, so a localization of covariance matrices around each particle. This is by Reich and Weismann. And it also worked reasonably well for multimodal failure domains. And what we can also do is we can actually analyze the mean field limit and continuous time limit of the particles, and this again follows the EKI analysis for inverse problems that was done by Claudia Trilling. And as a summary of that part of the talk, we construct a sequence of auxiliary densities to approximate the optimal importance sampling density. And the EKI or ENKF dynamics moves the particles to the failure domain. I also want to point out that this is actually an interacting particle system that is coupled by the limit state function, and I will come back to this in the next part of the talk. But what I find very intriguing and interesting is that we can actually leverage several analytical results for this Ensemble Kalman filter for inverse problems. And to my understanding, it's a very active area of research. There is one difficulty here that immediately comes up because, and this is due to the way how we construct this auxiliary limit state function. So in Bayesian inverse problems, you distinguish a lot between like a linear parameter for observable map and a nonlinear parameter for observable map. And the linear case is the case where you have quite a lot analytical results, and the nonlinear case is a bit harder to treat. Well, in our case, we always have a nonlinear inverse problem. Yeah, this is due to the application of the maximum. Yeah, so even if our limit state function g was linear by applying this ReLU function, essentially, we get a piecewise linear problem. So I mean, this is what I mean by piecewise linear. So maybe it's not so bad and not so nonlinear, but still, it's a different problem. Okay, so maybe I can now take the last 10 minutes or so to talk about another approach that we investigated recently, this consensus-based event estimation. And again, the idea is to move the particles that we have in an initial ensemble along the trajectories of some stochastic differential equation. So I didn't show you the SDE in the EKI case, but there is an SDE behind, and I have a slide on that near the end. Now, I mentioned already that the consensus-based rare event estimation is based on a consensus-based sampling method that was introduced very recently by Andrew Stewart and collaborators. And the SDE behind is the so-called Makin-Lazow SDE. So what you see here is two parts. You see a drift term that has this term m beta here that depends on the law of the stochastic process. This is why it's a Makin-Lazow. And then you subtract here the minus Vt. And then you have a diffusion term. So an n-dimensional white noise here that is scaled by some suitable covariance matrix. There is more parameters in this approach compared to the EKI. So here we have an inverse temperature, a beta parameter, which appears in this exponential here. So in terms of variables, yeah, this beta is now the inverse temperature. For the EKI, the sigma was the temperature, but they play essentially the same role. F is a so-called energy function, and well, here in this definition, mu is some probability measure, and in this Makin-Lazow SDE, this mu will always be the law of the process. And the Z is again a normalization function. And now maybe we can try and talk a little bit about what this is actually doing. So the key observation is that the law of the particles that I have here is always reweighted by this factor, this exponential, where I have minus the inverse temperature times a function f here. And if you now increase this beta, this has the effect that the probability mass of this process concentrates around the minimizer of f on the support of the law of the process. Yeah? And this has the effect that this drift term points towards the minimizer of that function f. And perhaps I can also mention that this consensus-based sampling you can also use for optimization approaches, and this is also what Andrew Stewart and co-workers proposed. So they use the CBS method to generate posterior samples, but they use the CBS method also to approximate the map point, for example, of an inverse problem. So, so you increase the inverse temperature, and then the drift term will automatically it will point towards the minimizer, and the particles will drift towards the minimizer of that function f. And the function f is now our choice. Yeah, that has to be chosen suitably. And this diffusion term, on the other hand, has the effect that the covariance of this process approximates the curvature of f near the minimizer. And this is very much in the spirit of a Laplace approximation of a measure with the density tau here. Yeah? And maybe if you know Bayesian inverse problems, you can see by this whole process can actually be used to generate posterior samples in a Bayesian inverse problem. So if you choose the f appropriately, you can make this work. Now, the difficulty with this SDE is that you have to discretize it in some way, and here we exactly follow the proposal by Carrillo, Stewart et al. So they use for the time discretization an exponential Euler-Maruyama type method, and the law of the process is approximated by particles with empirical means and covariance. Now the crucial point is how we actually choose this function f, and this function f that we use is again linked to the optimal importance sampling density that you see here. So if you recall, the optimal importance sampling density we are interested in is the standard normal density multiplied with the indicator function that indicates failure. And well, the f in the consensus-based sampling has to be a smooth function. That's why we use a smooth approximation of the indicator function that has another parameter s in here that controls the approximation quality. Yeah? And the idea is if we let this s parameter go to plus infinity, then this function p here approximates again the optimal importance sampling density. And now the energy function that we use in the CDF is minus the logarithm of p. And well, this CBRI method that Konstantin Althaus, our master student, developed now tells you how to choose the S, the time step size in the Euler-Maruyama discretization, and the inverse temperature adaptively. And the details for that, let me skip this, the details for that can be found in a paper that we submitted recently, and it's also available on arXiv. I think I mentioned this already. Again, we do experiments with a PDE-based limit state function in 1D physical space, and also in up to 50-dimensional parameter space. And we can compare this new consensus-based Ray event estimation method with sequential importance sampling and also the EKI or ENKF method that I talked about earlier. And the conclusion is that at least in low parameter space dimensions, this method is competitive with SIS and the ENKF method. For higher dimensions, it's not so effective anymore, and it's not so clear why this is the case. Yeah? But maybe let me finally show you the picture that I find very interesting, because now we can try and compare the EKI approach for the event estimation and this new consensus-based approach. So this is the example that you have seen before in a two-dimensional parameter space with this limit state function here that distinguishes failure and safe states. The ENKF particles that we get in the end are the green particles, and this is the feature that you saw before. So the ENKF dynamics forces the particles towards the failure domain, and they get essentially stuck on the surface. Whereas this consensus-based method actually has a dynamics so that the particles are spread out a lot more. And they look a lot more like optimal importance sampling density that we have. Yeah? The optimal importance sampling density that we want is the multivariate Gaussian density restricted to the failure domain. Yeah? And yeah, so this is something that the consensus-based sampling can evidently achieve, and it is also known. I mean, Andrew Stewart and collaborators investigated this. So if you start with samples according to a Gaussian density, and then you apply this PBS dynamics, you will stick with a Gaussian density. Yeah, and I think this is also what you can see. And now I think it would be really interesting to try and merge the dynamics of the two. But so far we haven't done this. And I think this is now my final slide. So I promise to show you at least the dynamics behind the ENKF iteration. Well, this is nothing new. This is adapted to our auxiliary limit state function. So, and basically I mentioned it already, the drift term vanishes inside the failure domain. So that is one difference compared to the consensus-based sampling drift. And also I would like to point out that here this noise term or the diffusion term is actually a scalar process. Yeah, so we have a scalar process here, then a scalar drift term, and then this is coupled or preconditioned, as some people say, by covariance of the process ut and g tilde of. And the EKI is then a discretization of this stochastic dynamic. And for the consensus-based sampling, the noise term is actually now a vector valued Wiener process, and it is scaled by covariance term and also the suitable drift term. Okay, and I think with this I can conclude, and let me point you to the papers. So the EKI paper, or the Ensemble Kalman for the Fourier event estimation, appeared last year in JUQ, and the consensus-based Ray event estimation you can find on arXiv, and Konstantin also provides the code that you use. So if you want to play around with this, you're very welcome. Take a look. And with this, I thank you for your attention. Thank you very much.
Thanks very much, Elisabeth. I assume you can still hear me, is that right?
Yes, that's correct.
Okay, great. I think we've got a couple of minutes for questions. Any questions? So Elisabeth, it sounds like it was perfectly clear. No questions here, apart from maybe something from me. It's a high-level question about the applications of your methods. You mentioned there was a civil engineering application. Is that right? That's the one that you were talking about?
Yes. I mean, in civil engineering, you would maybe be interested in the failure of a bridge, yeah? Or another example that is also frequently investigated in the UQ community is the leakage of a radio nuclear repository. Yeah, so you basically want to explore where you can safely store nuclear waste underground, and one main reason for nuclear particles to come back to the human environment is that someone accidentally drills into the repository, and the particles get released and transported by groundwater flow back to the surface or back to some human environment. And this is a simple PDE model, a random coefficient, and you would be interested in studying the time that it takes particles to travel back. And a particle that comes back after a very short amount of time, this can be considered as a failed particle. Yeah, this is the unsafe situation that we do not want. But maybe I can also say that we focus very much on the theoretical development, not so much the application.
Yeah, no, I understand that. No problem. It's just trying to understand a bit the physical process as well. It sounds like, oh, there's a question. Go ahead, Ben.
ENKF and the CBS, you said the ENKF gets stuck near at the failure boundary, but at the same time you said you better like what CBS is doing. But then when you say the zero variance density actually has that same property, right? That no particles are outside of the failure domain. So why do you like the CBS better than the ENKF if it seems to be closer to the zero variance density?
I mean, this CBS method creates ensembles that are more spread out and that look more like a Gaussian and that are actually Gaussian. And and like I said, this optimal importance sampling density looks like a Gaussian, but it is restricted to the failure domain. And with the ENKF dynamics, you don't get it. I mean, the particles, it doesn't look like it comes from a density that is Gaussian, yeah, because it really tries and follows this failure curve. But with CBS, you get more, the particles spread out a little bit more, and also in the failure domain. It looks to me like it's more Gaussian. This is what I meant.
Sorry, there is a question from the audience on Zoom. There's a Jonas, I think, has got a question. Jonas, are you able to ask your question?
Yeah, I think so. Can you hear me?
Yes.
I mean,
yeah, we
somebody.
can.
Okay, perfect. Hi, good morning. I was wondering, is there a natural way to introduce multi-level into the NKF or the consensus-based sampling setting by, say, using multi-level Makin-Vlasov ideas, or is that too difficult?
Thank you, Jonas. Well, we haven't thought about this, but like I said, in this talk there is no multi-level. But I could imagine that it would be a very natural question to introduce that, the multi-level idea. And I mean, the original like multi-level Monte Carlo method was studied by Mike Giles for STE. Yeah. Mm-hmm. I haven't seen anything on Makin-Vlasov STEs and multi-level, but that would be very interesting to do.
Great.
Okay.
I think we might. Thanks, Jonas. I think we might have time for a very quick question.
Just following the question that was before the last one. Yeah. Could you remind us, please, why it should be a Gaussian, this optimal sampling density. Is it related to the specific model, or I'm...
No, but yeah, thank you for the question. I'm happy to remind you. So maybe I'm still not expressing myself clearly. I apologize for that. But so this is the optimal importance sampling density. Can you see slide number 8?
We can no longer see the slide. No, it's okay.
No?
Yeah, we can't. Look, tell you what, Elisabeth, that's fine. I think perhaps, I guess if you were here, we could continue that in person, but if not, then maybe we could send you the question and you could provide an answer. But in any case, let's thank Elisabeth one more time for her talk this morning. Thanks very much. Thank you.
Thank you.